Google's TPU is the one serious counterweight to Nvidia's GPU empire, and over the past 2 years, it has clearly been picking up steam. Just look at the headlines. Anthropic signed a deal with Google for up to 1 million TPUs and over a gigawatt of compute, then came back this April for another 3.5 gigawatts of next-gen TPU capacity. Apple went even further. Their official paper spells it out. The foundation models behind Apple Intelligence were pre-trained entirely on Google TPUs. Even the two de facto standard open-source inference frameworks, VLM and SGLang, now have officially maintained TPU repos. So the TPU has gone from Google's in-house toy to a second ecosystem you can no longer ignore. And its design philosophy is very different from a GPU's. A GPU throws tens of thousands of small cores at the problem, plus a sophisticated hardware scheduler. A TPU bets almost all of these transistors on one giant systolic array that does matrix multiplication and pretty much nothing else. That difference propagates all the way up the stack and shapes every line of the inference code you write. I work with TPUs and jacks every day, so in this video, I'll use one concrete case study, VM's racked Pagged Attention kernel on TPU, to walk you through the TPU design philosophy, why it's fast, where its weak spots are, and how engineers work around them. Design philosophy sounds abstract, but one picture makes it concrete. Let's look at this architecture diagram. GPU on the left, TPU on the right. The GPU's approach is strength in numbers. A single chip has more than 100 SMs, or streaming multiprocessors, each packed with small cores, its own L1 cache and registers, and tens of thousands of threads running in parallel. On top of that sits a very sophisticated hardware scheduler that hands off work, queues threads up, and fills every idle slot. If one thread is stuck waiting on memory, another one jumps in. The TPU takes the exact opposite approach. The whole chip is built around one giant machine, the MXU, the matrix multiply unit. At its heart is a 256 by 256 systolic array that can do over 60,000 multiply accumulates per clock cycle. Everything else on the chip is a supporting actor. The VPU is an 8 by 128 vector processing unit that handles all the non-matchable vector work, such as element-wise additions and activations. VREX are the vector registers, also 8 by 128 each. Below that sits VMEM, an on-chip software-managed memory that the vector register loads from and stores to directly. Capacity-wise, VMEM is like a GPU's L2 cache. Usage-wise, it's more like shared memory. And off-chip, you have HBM, high bandwidth memory, on the order of 100 gigabytes. The hierarchy is clear. HBM, VMEM, VREX, then into MXU or the VPU. The scalar part is like the CPU, which we will skip. You can pause the video here to check the main components of TPU carefully. Two differences in this picture deserve a highlight because they set up everything else in this video. First, the compute granularity for TPU is large. The MXU has a fixed appetite. The minimum meal is an 8 by 128 block times a 128 by 128 block. If your data blocks are too small or oddly shaped, the machine runs half empty. So by construction, TPUs are unfriendly to racked workloads. Second, for TPU, execution is single-threaded. A GPU hides memory latency with tens of thousands of threads covering for each other. One waits, another computes. The TPU's tensor core is single-threaded, one worker following a script. When to move data, when to start computing, all of it have to be decided ahead of time by the compiler and the kernel author. The upside is predictable, deterministic performance. The downside, if the script is bad, the machine just sits there waiting. Here is an analogy I'll use throughout this video. A GPU is a construction site with 100,000 workers and the foreman constantly reassigning people. Anyone idle gets a new job. A TPU is a fully automated stamping line, fixed rhythm, enormous throughput, but extremely picky about the size of the incoming parts. And changing the parts back means retooling the whole line. So what kind of incoming material does this line hate the most? First, the word ragged. There is a mountain in Arizona literally called Ragged Top. Look at this ridgeline, and even all over the place. An LLM inference batch looks exactly like that. In the same batch, one request might be a few dozen tokens, another tens of thousand tokens. That is raggedness. And it's dynamic. After every decode step, every sequence grows a bit longer. So why is that a problem? The TPU software stack XLA is at its best with static, regular workloads. Fixed shapes, everything planned at compile time. Feed it a regular workload and two problems popped up. First, coarse grind tiling means padding. Short sequences get zero padded up to the fixed block size, so you burn compute on zeros. And you cannot tile the KV any finer even if you want to. Second, misalignment between access pattern and layouts. The layout is designed for regular shapes, so ragged access turns into scatter and gather, which are non-contiguous transfers, and the overhead shows up. Back to the stamping line analogy, the dies are fixed size. A batch of parts arrive in all different sizes, and the tiny part still occupies a full die slot. The rest of the slot are wasted. That is the TPU facing a ragged workload. Look at this figure. The green cells are the actual data and the gray ones are the padding. With a rack workload, many of the compute can be wasted. So what does this machine actually look like inside? Why is it so picky about shapes? Let's open up the MXU. The word systolic comes from the heart. Systole is the contraction phase of a heartbeat. Data flows like blood on a fixed beat through a grid of multiply accumulate units. In an m by k times k by n matmul, the model weights are preloaded into the array first and stay there. Input activations stream in from one side on each bit. Partial sums ripple down through the array, and the results stream out the other side. During the whole computation, nothing touches the memory. The data just floats inside the array. That's why it's so efficient. But this design has a hard constraint. The array is physically 256 by 256, and the utilization depends entirely on the shape of the matrix you feed in. Look at this figure, it lists 4 cases. Let me introduce two terminologies first. In a matmul, the contracting dimension is a k that gets summed away. The other one is the non-contracting dimension m. Actually, m is also a non-contracting dimension because it appears in the result. But that's related to the temporal thing, which we will skip. In case A, both dimensions k and n reach 256, so it's 100% utilization. In the other 3 cases, as soon as either side is only 128, half the array is multiplying zeros, and the utilization drops straight to 50%. And attention is exactly the operator whose shapes follow the requests. Once the batch goes ragged, the blocks you feed the MXU rarely line up to 256. That's the root of the whole problem. Irregular shapes, underfed machine, flops idling. Every optimization we will talk about is, at the end of the day, a way to keep this machine fed. So that was the machine, now the warehouse. How data is actually laid out in TPU memory. This section is a bit hardcore, but the two concepts coming up, tiling and packing, are the keys to understand everything RPA does later. Worth 2 minutes. First concept, tiling. The TPU split a matrix into fixed size tiles and store it tile by tile. Why? One reason is that the DMA engine that moves data around has a minimum transfer granularity, 512 bytes per transfer, which is 128 32 bits entries, which matches the tensor core width of 128. Tiles that are too small are not worth moving. Look at this example. A 32-bit float matrix of shape 8 by 256 with a tile of 4 by 128. Logically, you see a big row major table. It follows the order A, B, C, D, E, F, G, H. But physically, it is serialized into the linear memory following the tiled order. So here is tile 1, tile 2, tile 3, and tile 4. The order of these chunks are A, C, E, G, B, D, F, H, and so on, where each chunk is 256 bytes. The second concept is packing. For narrow data types, for example, BF16 only have 16 bits. In this case, putting one element in a 32-bit slot wastes half of the space. So the TPU packs elements from adjacent rows into the same 32-bit slot. Lower 16 bits from one row, higher 16 bits from the other. Let's compare these two figures. They are both 7 by 200 matrices. In float 32, each logical row takes its own row. In BF16, row 0 and row 1 are stacked into one physical row, row 2 and row 3 into another row. So these two physical rows actually face in 4 rows. The layout matters a lot for RPA. One more terminology before we move on. Dynamic slicing. It means cutting a chunk out of a big tensor where the start and the length are only known at runtime. Say you are grabbing a sequence valid region, start at token 137, take 42 tokens. That 137 and that 42 change every step. The compiler has no idea. With static slicing, the compiler pre-plans all the addresses and transfers. With dynamic slicing, everything is computed on the fly. And if the cut doesn't line up with tile boundaries, it gets even slower. Racked workloads are full of these. So RPA does two things when designing its data layout. Put the racked dimensions on axes that are not tiled, and put the packing on the second minor dimension. With that agreement, dynamic slicing, scatter, and gather, all the irregular transfers run efficiently without churning the physical layout every time something moves. In warehouse terms, everything is stored in standardized boxes. Pull material along the box direction, and one forklift trip grabs the whole box. That's fast. Try to pull sideways a little bit out of every box. Now you are opening boxes, digging around, resealing, throughput collapses. What RP does is stack the stuff that moves often in the forklift-friendly direction ahead of time. So we have addressed the issues in the machine and the warehouse. The one last piece of the hardware picture is the logistics. Remember that the TPU is single-threaded. No army of threads to hide memory latency for you. So how does it keep the machine from waiting on material? The answer is double buffering. Look at this figure. HBM holds the inputs X, Y, and the output O. In VMAM, every piece of data gets two buffers. While the tensor core is computing for block I, the DMA engine is simultaneously pulling block I plus 1 from HBM into the other buffer and shipping block I minus 1's results back to HBM. When block I finishes, the two buffers swap roles. Seamless. Compute and data movement fully overlap, and the machine never stalls. You can write this pipeline in Palace, which is the JAX kernel language. Think of it as Triton for TPUs. Palace has a nice default. If you don't explicitly control, the XLA compiler auto-generates a multi-buffered pipeline for you. But RPA switches to manual mode and takes over the entire pipeline explicitly. It allocates its own double buffer in VMAM, issues its own DMAs, manages its own semaphores, and goes all the way down to the register level, using bit operations in VREX to unpack and pack K and V. Why go through all that trouble? Because racked shapes are dynamic, and the auto-generated pipeline cannot handle irregular cases. If you want every last drop of performance, you write the script yourself. Same production line. It's a one-person operation, but with a conveyor system. This batch is being stamped, the next batch is already on the belt, and the previous batch is rolling out the door. RPA's whole job is to be its own dispatcher and tune that rhyme to perfection. So now the hardware part is all covered. Time for the main character. First, let's introduce VLM's Pagged Attention. During LLM inference, every sequence keeps a KV cache that grows as it generates. Reserve a big contiguous chunk of the sequence and you will get terrible fragmentation and massive memory waste. VLM borrowed the paging idea from the operating system's virtual memory. Chop each sequence KV cache into fixed-size pages, allocate on demand. Pages don't need to be adjacent in physical memory. A page table records where each sequence pages live. In this figure, request A's and request B's pages are interleaved all over the cache pool. and each request follows its own arrow to collect its own pages. Memory utilization goes way up. This is one of the core reasons VLM gets its throughput, because with this, it can hold more requests. But you have probably already seen it coming. If we apply this on TPU, it will be very bad. There are two challenges here. KV reads become gathers. A sequenced pages are scattered everywhere. So reading means collecting data from many non-contiguous addresses. On the other hand, KV writes become scatters. During decode, each sequence adds one token per step, and that small amount of data need to append it to a half-full page, which is fine-grained, fragmented write. Recall that the TPU's DMA like moving the whole boxes, and MXU like big regular blocks. Pagged attention makes them spend all day running around the warehouse, picking up loose parts and squeezing single items into half-full boxes. Moreover, it gets worse with mixed batches. In real scheduling, prefill and decode run in the same batch. Look at this figure, there are 4 requests. Squares are prefill tokens, circles are decode tokens. The scheduler packs batches under 2 limits. At most 6 tokens and at most 3 sequences per batch. And for every batch, it can produce a different length and different mix. Whatever doesn't fill up gets padded. So this is the ragness in its final form. Shapes that are not just irregular, but changing every single step. So now we have the 4 problem list. Gather, scatter, dynamic shapes, padding. Every one of them is a TPU weak spot. Now let's watch RPA counter them one by one. RPA, Racked Pagged Attention, is VLM's attention kernel on TPU. It proposes 3 techniques to address the issues above. Number 1, fine-grained tiling. It introduces a packing dimension so the tiling is finer than XLA's default, which kills padding at the root. Number 2, a KV update fused pipeline. It forces the KV cache update into the pipeline, overlapped with the attention compute. Number 3, distribution-aware compilation. Requests with different length distributions get different specialized kernels. And after introducing these 3, we'll also briefly cover some practical notes for tuning and quantization. Remember the TPU's 2 weak spots: coarse granularity and the fear of anything dynamic. The first 2 here attack granularity, while the third attack the dynamic part. Let's start with some background in XLA. On a TPU, you don't get to decide how data is tiled and padded. XLA does. There is a pass in XLA called layout assignment, and it looks at exactly 2 things: tensor shape and data shape. Then it will use that to decide tiling and padding. You want a finer 1 by 128 tiling? If XLA decided a 8 by 128 tiling, you don't get a vote. This causes 3 problems. Problem 1, the loop dimension gets tiled. Look at the attention's inputs. Q has a shape BT, N, H. BT is the total number of tokens flattened in the batch. N is the number query has, and H is the head dimension. K and V shape are BT, KH, where BT and H have the same meaning, and K is the number KV has. So here is a symbol table in the figure. Feel free to pause and check it. Although in the figure, we don't flatten the tokens. So batch and sequence length are 2 separate dimensions. So XLA tiles the last 2 dimensions by default, which for KV means K and H, the number KV has and head dimension. But K is the dimension the kernel loops over. Attention is computed 1 KV head at a time. Tiling it is pointless and actively harmful. The natural fix is to transpose it to the front, which makes it K, BT, and H. Problem 2. BT is dynamic. The token count changes every step, and dynamic slicing on a tile dimension means unpacking, blending, and repacking, which is a whole combo of wasted work. Problem 3. Head dimensions are small, which can trigger implicit padding. Modern models love MQA and GQA. Many query heads sharing 1 KV head, so the number of KV heads are small to begin with, and the tensor parallelism slices them down further. Per chip, you end up with very few heads. and small head counts hurt. With a 8 by 128 tile, a BF16 tensor of 12 by 128 get batted to 16 by 128. A third of the compute is wasted. With a finer tiling like 2 by 128, the waste will disappear. So how does RPA break out? The idea is good. If you cannot change XLA's rules, change your data shape so the rules work for you. The solution is to manually add the packing dimension to QKV and place it at the second minor position. With this change, the layout that XLA automatically assigns is exactly the fine-grained one that RPA wanted all along. In warehouse terms, the automated stacking system only looks at the shape of your cargo and its decisions are final. And our solution is to repack the cargo. Same goods, different box shape, and now the system own rule produce the layout you want. How exactly to repack is the next two sections, one recipe for Q, another for KV. Let's do Q first. RPA performs two operations on it. Step 1. Group N query heads by KV head. In JQA, every G query heads share one KV head. So we have N equals to K times G, where K is the number of KV heads. After that, we insert the packing dimension PQ at the second minor position. Step 2. Transpose the K dimension to the front, because it's a looping dimension. The result is a 5-dimensional tensor. K, the number of KV heads, BT, the number of flattened tokens, and G divided by PQ, then the packing dimension and the head dimension. Pause here if you want the details. In summary, the idea is that query heads in the same group sits next to each other in memory. Packing sits at the second minor, and the tiling XLA hands back is automatically fine-grained. This leads to the payoff at compute time. Then, when a Q block is loaded into VREX, it's viewed as CQGH. The G query heads of a group line up in the queue and take turns against the same CK and CV. Remember in section 3, model weights get loaded into MXU and stay there? Same principle here. K and V are installed in the array once, and the whole group of queries flow through. Now K and V. Here the situation is even more extreme. MQA or GQA plus TP sharding, the per chip KV head count often drops to exactly 1. And BF16 packing is 2. Each 32-bit slot wants 2 rows. One head fills half of the slot. The other half is permanent padding. Half the space is gone. And in RPA, since K and V has the identical shapes, it merges them into one tensor along the high dimension. So they are interleaved. In each 32-bit slot, the low 16 bits holds K, while the high 16 bits holds V. Slot is full and there's no waste. The cost is unpacking at use time. Load the 32-bit value, then split K and V back apart with bit operations we mentioned. As long as unpacking stays off MXU's critical path, the overhead is completely hidden. FP8 data type is messier. One 32-bit word holds 2 KV pairs, so extraction is repeated and costs more. Overall, the trade is clearly worth it, especially for decode. The smallest update unit, a single token slice, carries K and V for all KV heads at once. One DMA delivers everything. No separate trip, one for K and one for V. There are two other benefits. The number of vector loads and stores is cut in half, and the effective DMA transfer size doubles. One last question for this approach. Who produces these custom RPA layouts? The ideal answer is to process them offline. We pre-shuffle the projection weights WQ, WK, WV ahead of time, so that when the model runs its in-sum, the Q and the merged KV that comes out are already in RPA layout. But that road is closed. The reason again is XLA. Layout assignment only respects the layout at kernel boundary, which are inputs and outputs. Intermediate tensors get reordered however XLA please, and user-specified layout constraints get overridden. However carefully you arrange things offline, a few intermediate ops later, your layout could be quietly replaced. So XLA defers this transformation to preprocessing. in order to guarantee layout integrity. Back to the warehouse analogy. You wanted the goods packed to the warehouse back at the factory, but every transfer station along the way insists on repacking the boxes its own way. That's fine. We accept it and repack one last time at the destination door. Looking ahead, there could be three alternatives. We can write a dedicated projection kernel that locks the layout, but the ops between the projection and RPA may still reorder. The second one is to fuse projection into the RPA kernel, so the layout never altered. That's a complete fix. And the last option is to wait for XLA to someday propagate user layouts into custom kernels. If that happens, the pre-processing step can be deleted entirely. Okay, so that's the end of the first part. Data shape and placement are all set, but a good layout is just the start. Making the machine and the logistics run without a single gap, that's the pipeline, which we'll introduce right now. So in the previous section 5, we covered the principle of double buffering. Now let's see RPA's real pipeline. There are two families of symbols to recognize. The B's, BQ, BKV, BO, are transfer units. They are the big chunks one DMA moves from HBM to VMAN. And the C, CQ, CKV are the compute units. These are the small blocks loaded from VMAN into VRAX and fed to the MXU. A truckload arriving at the factory is a B, and the several trays that goes onto the machine are the C's. There are 4 types of DMA ops in the pipeline. Moves a Q block from HBM into VMAN, but only for the effective token range. Fetch BKV. Follow the page table and gather the scattered PV pages into one contiguous block in VMAN. This is where the gather problem from section 6 gets digested. Update UKV. Write the newly projected KV back to the KV cache in HBM. And finally, send BO. Ship the finished output block back to HBM. While DMAs are moving, 5 compute stages are turning. We load the compute CQ from the transfer unit BQ into VRAX. Then strided load CKV out of BKV, which also complete the transpose step, and we will introduce more in the next section. Then we will unpack it into CK and CV in the registers. And using CQ, CK, CV, we can run flash attention. Finally, we store the output CO into the VMAN buffer BO. The transfers and computes are overlapped, and this is the double buffering, and you can check this figure for the details. Next, the KV transpose fusion. Recall that we said K and V should be transposed to put K up front, and we also said that transpose never actually runs. Now let's discuss how this is achieved. KV transpose is fused into the data load. So here is the logic. The K dimension is only there to loop over. It takes no part in the matmod. So there's no need to physically transpose the data in memory. That would cause a whole extra round of data movement. Instead, when loading from VMAN to registers, concretely, after the KV block lands in VMAN, we view it as one logical table with BKV times 2K rows and H columns. And then we'll do strided loads. We grab one row every 2K rows. So the data lands in the register are already in the transposed layout. There are 0 extra transfers and the transpose is free. But one caveat is that VMAN is internally divided into banks, and an unlucky stride hits the same banks every time. Like a supermarket with 30 checkout lanes where everyone lines up at the same one. The fix is simple. We add a small offset in the VMAN block layout so that the effective stride is odd. An odd stride cycles through all the banks and never have conflicts. So the DMA's effective transfer size is not affected. Now for the other problem left over from section 6, scatter. Every deco step, every sequence produces exactly one new token and with its KV cache, which has to be written into some half-full page or a new page. Running a dedicated DMA for that tiny amount of data would be a terrible deal. So RPA hides it. The new KV writes along with fetch BK. While gathering the old pages, append this new step's new KV at the tail of the same VMAN buffer. Attention needs to compute over it anyway. It was coming in sooner or later. The write back is also along the way. Update UKV reuses that same buffer, asynchronously writing it back to the right cache pages, fully overlapped with the attention compute. So the KV cache update needs no separate kernel and no separate rounder transfers. Decode single token updates get handled inside the pipeline. That's where the KV update fuse in RPV's move to gets its name. Back to the production line analogy. When the truck goes to the warehouse for the old material, the newly arrived parts ride along into the workshop and go into the same bin. While the press is stamping, the updated part of the bin ships back to the warehouse on the return trip. From start to the end, not one dedicated truck run for that single new part. And now move 2 is done. Transfers and compute are overlapped tightly. Both gather and scatter have been folded into the pipeline. But one big problem remains. The workload shape is dynamic and the compiler demands static shapes. So let's move on to the next section, the move 3, distribution-aware compilation. This is to tackle the dynamic issue. The root of the problem is that the TPU's tensor core runs single-threaded with a script, and when the compiler unrolls a compute block, it must statically decide how many VREGs to use. That script can only be written for the worst case. Assume every sequence Q length might be long, but the decode Q length is always exactly 1. If we unroll for the worst case, then most of the registers and computes sits idle. So RPA's solution is that if one pod cannot serve everyone, we cook in separate pods. The scheduler first stores the request in the batch, then passes 3 boundary indexes I, J, and K into the kernel. 0 to I in the batch is for decode only, where the Q length is fixed at 1. I to J are fixed size chunked prefill, so the Q length is also a compile time constant. And J to K is the hardest mixed workload, and all the truly dynamic lengths live here. This ordering is guaranteed by a post-scheduling reordering algorithm. All decode-only and fixed prefill requests go to the front. Then we have per-case specialization. We compile up to 3 specialized kernels and run them back-to-back on the same batch. The decode kernel and the prefill kernel know their query block size at compile time, so VREG usage and compute scheduling can be planned optimally. Only the mixed kernel still have to leave room for unknown lengths and eat some padding waste. Think of it as splitting the factory into 3 lines. One for standard small parts, one for standard large parts, and the only odd-shaped pieces go down to the slower but flexible line. On the other hand, JIT enforces static shapes, so what should we do with it? The solution is simple. We set upper bounds. RPA fixes max number of tokens and max number of sequences, and pad every input to those caps. Then the shapes are identical every step, which means 0 recompilation while serving. And with that, all 3 moves have landed. We call our problem set in section 6. Gather, scatter, dynamic shapes, and padding. Every item now has an answer. Gather and scatter get fused into the pipeline. Dynamic shapes get the separate post-treatment. And padding got mostly erased by fine-grained tiling. So now all 3 moves are done. Let's briefly talk about 2 engineering footnotes. First, tuning. RPA exposes 4 tunable block sizes. BQ and BKV set the transfer batch size. You tune them to overlap DMA and compute more tightly. CQ and CKV set the compute block size per trip to the machine. You tune them to keep VREG pressure down so the registers don't overflow and spill. But there's no universal gold setting. It depends on 3 things: the TPU generation and the topology, the model specs, such as head dimension, context length, and the workload distribution. So there's one set of parameters per workload type. For decode only, it's memory bound, so we mainly tune towards saturating memory bandwidth. For prefill only, it's compute bound, so we tune towards maximize MXU utilization with minimal scaling. And the mixed workload is the hardest one. We tune for the common case. For example, If in production most requests have short KVs, we tune for short. And the recommendation in the paper is that we can tune it offline, store the results in a lookup table, and apply it at server bring up. Second footnote, quantization. RPA currently supports per tensor quantization, which is one scale for the whole tensor. Per channel and per head are not supported yet, so this is some future work. Alright, that's the whole story. Let's have a quick recap. We started from TPU's design philosophy. Nearly all of its transistors bet on one 256 by 256 systolic array, and it has single-threaded execution with a predefined script, essentially a fully automated stamping line with a fixed rhyme, enormous throughput, and zero patience for odd-shaped material. LLM inference batches are the opposite, racked and changing every step. And once Pagged Attention chops KV into pages, gather and scatter, the TPU's least favorite operations become everyday work. RPA's 3 moves handle these conflicts piece by piece. Move 1. Reshape the data. Add a packing dimension so XLA's own rules produce a fine-grained layout. Padding eliminated at the root. Move 2. Fuse the pipeline. Transpose is folded into the load. KV update is folded into the fetch and write back. Transfers and compute are overlapped with no gaps. Move 3. Compile per case. Specialized kernel for decode only, prefill only, and mixed workload. This translates the dynamic world into the static shapes that the machine loves. If I have to compress it into one line, performance work on TPU is the art of shapes. You cannot change the machine, so you change the shape of the data and the rhyme of the feed and keep the machine full at all times. This mindset applies way beyond attention. It's how you write any kernel on a TPU. The TPU ecosystem is moving fast. VLM and SGLang both have official TPU repos now. Anthropic and Apple are betting real money. If you work on inference optimization, getting on board now isn't early and it's definitely not late. That's all for today. Thank you and see you next time.